All right, everyone. We're here for the last class of the semester, and then we'd have a final next Thursday, right? We've already been through this. Make sure you're here at 12:30, camera, all that good stuff. Bring your homework to the final. If we have time at the end today, I'll do it, but I actually want to do a lot today. So just so you know, I'm expecting a phone call for a delivery that they got to let me know they're coming. So I need to answer the phone. So just so you know, if my phone rings, I'll just tell you, oh, hey, hold on real quick, just to let them know I'm here. Okay. All right. So let's cover a couple of things. The first few topics that first few things I'm going to cover are going to be relevant to the final. And then if I have some time, I want to show you a little bit more, kind of leading you into Cal 2. So without further ado, let's do it. Any questions before I begin?
I do have a question.
Yeah,
Sorry. Are you gonna have like a what's it called? Like an answer key for the review exam things, or?
I'll probably give you the solutions to one of them, not both of them though.
Okay.
Yeah. I think I'll give you the one that's handwritten. The one that, yeah, the one that's handwritten, I think, that breaks it down like by sections. By the way, on the test, I won't put like what sections things are from. That's just to help you study. I'll give you the solutions to that one because I think I already have them made. So, all right. Okay, so let's talk a little bit about a certain type of problem that's on the review, and it also appears in the homework section for 4.7. And that is something like this. If you're given that the derivative of some function is equal to, let's say, 2x plus 1, and then you're also given that the derivative at 1 is 5, and you're also given that the original function at, let's say, 0 is 3, then can we find the original function? Okay, so this is the way it would appear. They give you a bunch of information, they ask you to find f of x. So I want you to think about what this is. They're giving you the second derivative, right? They're giving you that. Then they're telling you the value of the derivative at a point. Not the value of the second derivative, the value of the first derivative at a single point. They give you one piece of information about the first derivative. And then they'll also give you the value of the original function f at a point. Okay, so we know everything about the second derivative, right? Here's the function. We know everything about it. We know one thing about the first derivative, and we know one thing about the original function. And the question is, from that, can you recover the original function? So let's start grinding away. Let's see. Well, if we want to find the first derivative, right? If we want to find the first derivative, that would be the antiderivative of the second derivative, right? Because we're going to go backwards. So it's like, here's the second derivative. We're going to go backwards to the first derivative and then backwards to the original. And to do that, we have to use the integral. That's my integral symbol, right? We're going to do antiderivative to go backwards. So I'm going to take the antiderivative of 2x plus 1 dx. That's all the new notation we had from last class, right? So the antiderivative here, we would do them individually because they're separated by addition, and these should be easy antiderivatives. First one is just x squared. The second one is just x. And then we have plus some constant that we don't know, right? Always remember the constant. So that's what I know so far. Here's what I can tell you about the first derivative. The first derivative is equal to x squared plus x plus c. So it's a family of functions, right? The way I want you to think about this is What we know right now is that the answer here, this derivative, has to come from some family of functions. They all look the same. Remember I showed you all the pictures of the family and they all kind of look the same? The question is, can we nail down exactly which one it is? We can, because they gave us an actual point, right? They gave us this information. They're telling us that this 0.15 lives on one of the functions. So that means if I go to the right one and go up 5, wherever 5 is, that's going to land on exactly one of these functions and only one of them. And so this should be enough information for me to recover the function. It's really simple to do it. Watch, here's what I'm going to do. I know using the fact that the derivative at 1 equals 5, that tells me that when I plug 1 into the derivative, right? When I plug 1 in, it should spit out 5. Well, here's the derivative. Let's plug 1 in for x. We don't know what c is, right? We don't know what c is, but we know that this needs to be equal to 5, don't we? And so the left side becomes 2 plus c equals 5. And then you just solve for c. C is 3, subtract 2 on both sides. So now I know what the c is, but I can only recover c because they gave me this information. If they didn't give me this, I wouldn't know what c is, right? But now I do. So now I'm very, very confident that the first derivative is equal to x squared plus x plus 3. Okay, there's my first derivative. But that's not what the question is asking for, right? The question is asking for the original function. So what I'm going to do is the same exact procedure, right? Do it again. But now I'll use this information about the original function because I'm going to get a plus c again. And so I'll use that information to nail down exactly the f. So here we go. I'm going to say that the original function is going to be the antiderivative of x squared plus x plus 3. Are there any questions? So antiderivative now. So it's been a whole 48 hours. You've had time to master this now, right? You're all masters of the power rule for antiderivatives?
Yeah, of course.
Thank you. Thank you. Now I'm going to say plus c again, right? Plus c again. Now, I'm actually not going to use c. I'm going to use a different letter. I mean, I could use any letter. I'm going to use d only because I don't want you to confuse this c with that c. They're different. They're going to give us different numbers. So it's just some constant, right? Normally we call it c, but because we already have a c in this problem, I'm going to use d. Okay, so we know the original function. We know it's a cubic function, right? I know that. I know it's cubic. It's just which one is it, right? I need to figure out which of the family members it is. So we say, all right, well, using the fact that they told us that the original function at 0 was 3, we know that when we plug 0 into this function, well, that's nice, isn't it? Isn't plugging 0 nice? You get 0 cubed, 1/2, 0 squared, plus 3 times 0 plus d. That should spit out 3. And since all of these go away, all you have is d is 3. And so we have our final answer. Our final function is 1/3 x cubed plus 1/2 x squared plus 3x plus 3. There it is. Now, this is actually kind of amazing if you think about this. All right, this is pretty amazing because one way you could think about this is this. Let's say that we have some object and I know its acceleration function, a of t. Okay, let's say we know the acceleration function. Okay, check, we know it. All right, someone gives us the acceleration of something. And then they also tell us the velocity at some point, right? So they give us the velocity, I don't know, at 1 or something, and they give us, I'll just say at some number, and they tell us that it's some number. And then they tell us the position, d of some number is something. So in other words, they give you the acceleration function, then they tell you the velocity of the object at one point in time, and then they tell you the position of the object at one point in time. What can we then recover?
Basically all of the formulas.
All of them, which means you'll be able to tell me. So let me just restate this again. Think about it this way. The second derivative, think of it as the acceleration, right? It's like they gave us something about acceleration. Then they told us one thing about the velocity and one thing about the position, right? And from that, we recovered the velocity function, right, the derivative, and the original function, which is the position function. So someone gives you acceleration, one piece of information about velocity, one piece of information about position, and then you can tell them exactly where that object is at every point in time, and its speed or velocity at every point in time. That, to me, that's always been amazing, that it seems like you would need to know more than just the acceleration and two pieces of information to be able to tell me exactly where some object is at every point in time, but that's all you need. All right, it's pretty cool. All right, I have
That's
another
really
one.
cool.
Another one. How about this? How about I tell you the second derivative of some function? Did we use t or x there? X? We used x. We'll use x again. Let's do the same one. It was 2x plus 1, right? I'm going to give you that. So if this is true, right? And then I tell you this. F of 1, let me go look at the problem I just gave you. F of 1 is 5. F of 0 is 3. Find f of x. So am I losing my mind here last day of class? Did I just give you the same problem or no?
Well, you gave us 2 points on the original formula instead of one of them being on the first derivative.
That's right. There's a difference here. See this right here? I gave you some information about the original function, not the derivative, right? And didn't we need that? Didn't we need that right here? This f prime of 1 is 5. Didn't we need that right here to get what f prime was? We needed it, didn't we? I'm not giving it to you this time. So instead of giving you the acceleration function, think of it this way. Instead of giving you acceleration and then telling you one thing about the velocity and one thing about the position, I'm now giving you acceleration and I'm giving you 2 things about the position and no information about the velocity. And the question is, can we still come up with the position function? Yes, we can. Watch. It's actually pretty cool. All right, so first things first, let's try and find the first derivative. And to do that, we need to take the antiderivative of 2x plus 1, which we've already done, right? That was x squared plus x plus a constant. We don't know the constant, do we? We don't know it. And we're never going to know it because, well, not never. We're not going to know it right now because we are given no information about the derivative, right? Nothing, right? So, all right, what do we do? Well, let's just try and find f now by taking the antiderivative of that answer. So let's take x squared plus x plus c, which we don't know, and let's find the antiderivative of it. The antiderivative of x squared is 1/3 x cubed. The antiderivative of x is 1/2 x squared. What's the antiderivative of c?
Isn't it cx?
It should be that c times x, right? Because we don't know what c is, right? If let's say c was 5, then the antiderivative would be 5x, right? If it was a 2, it'd be 2x. We don't know what it is, but here's what I can tell you. Whatever it is, it's c times x, right? But it's still an antiderivative here, so we have a family. So I have a second variable here plus d. That's that constant I don't know. Got it?
Yeah,
Now what? So now
Now-
we're going to use the points, right?
we should substitute the 0 first so we can find D.
Yeah, we're going to use, I'm going to do it 2 different ways. I'm going to do it this way. I'm going to do it just in the order, just so we can see what's happening. I'm going to use the fact that when I plug 1 into this function, I should get 5, right? When I plug in 1, I should get 5. So that means when I plug in 1, I should get 5. Now, let me clean this up. This is just 1/3 plus a half plus c plus d is 5. And when you look at that, you should recognize that you have a single equation and you have 2 unknown variables, right? You have 2 things you don't know and you have 1 equation. Okay, great. Well, let's just wait. Let's now go look at the other one. Let's use the fact that we know that when we plug 0 in, we should get 3. So if we plug in 0 into this, we should get 3. And luckily for us, right? Luckily for us, everything here goes away except D, right? Which means that D must be 3. And once I know what D is, I can plug it in here and solve for C, right? So I can take this and make this 1/3 plus a half plus C plus 3 equals 5. Now look, this problem happened to work out real nice because we could get D, all right? But what if we would have not had information at 0? Like, let's say they told us f of 2 was 3. Then we would have to plug 2 in here, right? And this C term would not go away. But what you would have is 2 equations and 2 unknowns. And so you go back to college algebra and you'd set up a system of equations and you would either use elimination or substitution to solve this system, right? So I'm not going to do that. I'm just telling you what could happen. All right. In this problem, it's not happening. So let's see. Well, let's solve for C. I'm going to go ahead and put those 2 together. What is that? 5/6. And we get a common denominator there between those. Plus C equals 2. I subtracted 3 on both sides. I need to subtract 5/6 from both sides. And so C is 6 on top of 12, 6 minus 5/6, which is what's happening today, 7/6. There you go. So that's it. I know what f is now, right? My original function is 1/3 x cubed plus a half x squared plus c, but I just said c was 7/6, 7/6 x plus d, but we saw that d was 3. That is the precise function that we're looking for. All right. That should help you with the problem on the review. Let me see here. Where is it? Thought I downloaded it. Yeah. Number 15. I give you the second derivative of a function And then I actually give you information about the derivative and the original function. So you should be able to use this to get C off the first antiderivative. Then you should be able to use this to get the next one. So this should work out like the first one I did today. Okay. All right, let's do some more of what we were doing last class, which is some substitution. Let's do some more of those. So remember last class we were saying, all right, what is the technique that we have to try and find the antiderivatives? By the way, I should show you my notes for this. This will kind of recap what we did yesterday, or sorry, 2 days ago. If we were given a function f of x and we wanted to find the antiderivative, then this is the notation we would use, right? I wrote that down. I said, this is the notation. Little f of x here, here's capital F, that's the antiderivative. And then I told you what each of these things is called. This thing is called the indefinite integral. This symbol is called the integral sign. The function itself is called the integrand. That little dx is called the differential. The capital F of x is actually the antiderivative. And then the plus c actually has a name. It's called the constant of integration. So do not forget your constant of integration. It's always going to be there when you do an antiderivative.
Quick question.
Uh-huh.
Why is there a white line in the D on in the differential?
It's the syntax of the program I use to code this up. For some reason, it uses a double struct lowercase d. I don't know why it's always done that.
Okay, so that's
yeah.
just a thing because of the program. That's not an
It's
actual
the program, yeah. I use Wolfram Mathematica to do all this. And so when I tell it to insert an integral, that's the dx it uses. I could, if I wanted, just make it dx there. Same thing. All right, the process of finding antiderivatives of functions is called integration, right? Whenever we're finding antiderivatives, it's called integration. When you take derivatives, that's called differentiation, right? Differentiation is taking derivatives. Integration is finding antiderivatives. All right, so we already talked about the power rule last class. We said if we ever have the antiderivative of x to the n, we are in business. We can handle it. And there's two ways to do it. Well, not two ways, there's two cases. If n is not -1, we've got the good old power rule, right? We talked about that last class. If n is -1, well, that's the special case. It's natural, the antiderivative should be natural log of x. Now, most textbooks will put an absolute value around that x, and that's because you can't plug negatives into the natural log function. So by putting an absolute value, you expand the domain out further. So in Cal 2, be ready for that. If you're in Cal 2 and they say, what's the antiderivative of 1 over x dx, your answer will be natural log of the absolute value of x plus c. All right, now, I told you about substitution, right? And it's like there's kind of I don't know if you like steps, there's kind of steps, but it's not something, it's not as straightforward as product rule, quotient rule, chain rule. You have to think, you have to try things, I always tell my Cal 2 students, in Cal 2, you have to be ready to fail more times than you succeed when you're learning. Okay, you have to be willing to try something, it not work, you crumble up your paper, throw it away, and move on to the next, try something different, right? You're gonna strike out 100 times before you hit a grand slam home run, all right? So it takes time and practice. So for those of you who are going to Cal 2, I always say, like, I have a student right now in my Cal 2 class. He was a really good Cal 1 student, really good. Really didn't have to study that much. It was just kind of natural. And Cal 2 just ate his lunch because he wasn't used to working hard. He wasn't used to practicing. And in Cal 2, you have to practice. There's just no way to do it without practicing. no matter how good you were in Cal 1, like you see 1 or 2 examples in Cal 1, you're like, yeah, I got it, man. Product rule, I got it. Fine, if that's you, great. In Cal 2, you need to practice because it will humble you very quickly, all right? So this rule here, substitution, it's an idea, it's a strategy, okay? So the strategy that I explained last class was you look at the integrand, okay? That's the first thing you do. Just look at it, kind of think about, what do I have here? What do I have? You're trying to find something, okay? So you're trying to identify somewhere in there something. I don't know what it's going to be, but it's going to be something. And you're hoping to also see its derivative there, right? That's what I told you last class. Now, the derivative, I did not tell you this part last class. When you're looking for the something and its derivative, the derivative part needs to appear in the numerator, and it cannot be trapped. So it can't be like underneath the square root. It can't be within a parentheses that's being raised to a power. It needs to be isolated by itself. All right. Also, the derivative that you're looking at might be off by a constant, and that's okay. It's okay if it is. Now, as soon as you've established that kind of pattern of what you're seeing, then you make the substitution, you let u be that something, and then you go for it, all right? And you see what happens, all right? So that's the general strategy. Let's do one. I did a couple last time, so we're just gonna pick up where we left off. What the heck? Point there. I'm always afraid to go too hard too soon on this substitution. So let's start off with baby steps here, okay? With a baby step problem, I guess. So how about this? Yeah. Yeah. How about this? Cosine x over 1 plus 2 sine x dx. So you're looking around, you're looking for something. So I'm not going to ask for volunteers here. I'm just going to call on somebody. And I'm really hoping that they don't see it, because then we can think through it. All right. So Arturo, you want to go for it?
Can't you just substitute the denominator?
The whole denominator? You want the
Yeah.
whole thing?
Yeah, the whole thing.
Okay, so let's try it. Arturo is going to go with the whole denominator. Ambitious. Okay, let's see. What is the derivative of that? So here's where you take the derivative with respect to x of this. So the derivative of 1 is nothing, right? 0. Plus here, derivative of 2 sine x is 2 cosine x, right? Now, when I'm looking here, 2 cosine x, do I see 2 cosine x somewhere? I see cosine x, right? And is the cosine x in the numerator? Yeah. Is it trapped? It's not under a square root or anything, right? It's free. This is looking good. I don't have a 2 though, do I? So I'm off by a constant. That's okay. This is good. This is gonna probably work. So let's now do this. Every single time I do this, every time when I do the derivative du dx, every time my next step, I'm going to multiply both sides by dx. Every time. Every single time. So that means that from now on, I'm not going to show this step. I'm just going to write du, and then I'm going to write the derivative of this, and then I'm going to throw dx on the back. All right. I like to think of this as like a matching game. It's like you're trying to play a matching game at this point. I'm going to take the original integral and I'm going to rewrite it as 1 over 1 plus 2 sine x times cosine x dx. So this is why it was important that the cosine was in the numerator and not trapped, because I need to be able to slide it off to the back of the integrand like this. And do you see now this cosine x dx is that piece right there exactly? Right? I just don't have the 2, but that's okay because this is an equation. I can multiply both sides by 1/2. And now I do have cosine x dx by itself, right? So that means I am going to be able to replace all of this, right? I can replace it with 1/2 du. Got it? Further, the Arturo told us to do the substitution 1 + 2 sine x. That's this, right? That's going to become u, right? U. So let's rewrite the integral. I'm going to make the substitution now. I'm going to rewrite this. It becomes 1 over. The whole part in blue turns into u, right? So u times, and then the whole part in yellow turns into 1/2 of du. And I can kind of look at it this way now. Now, important question here. When you take derivatives, when you have constants attached, when you're taking derivatives, they come for the ride, don't they?
Yeah.
Same with antiderivatives. The constants come for the ride when you do an antiderivative, which means that when you get to this step, you are always allowed to pull a constant out of the integral. So I'm going to take the 1/2 and put it to the outside. That is allowed always, as long as the 1/2 is a constant, or as long as whatever it is a constant. You can never pull something out that has a variable in it because, well, for the same reason you couldn't do that when you were taking derivatives. You couldn't just ignore part of it because you didn't want to feel like dealing with it. Now, this right here is a new integral, right? It is written in terms of u instead of x, but I know the antiderivative of this, right? This is something that should look familiar now. This is very similar to
Isn't that the natural log?
this. Yeah, like if this was a problem that I put up just a minute ago, this would be a natural log absolute value of x plus c, right? That's kind of the generic formula we have here. All this is just replace the x's with u's and it's the same thing, right? So this should be the 1/2 out front comes for the ride. Natural log absolute value u plus c. And we're not done. Why aren't we done?
We need to put our substitution back.
Yeah, you got to go back to what it was, right? Like, I like to think of it this way. The original problem was in terms of x, right? And right now our answer is in terms of u. So that would be like me asking you, hey, what's your favorite color, right? And you're like 27. You know, it's like, wait a minute, 27 is not a color. Like, you've given me an answer that has nothing to do with the original problem. The original problem had to deal with x, and now you're talking about u's. We're not talking about the same thing anymore. So you need to get u back to x. So all you do is just replace u, right? This was u right here, right? So just replace it. 1/2 natural log 1 plus 2 sine x plus c. Box it up. Hey, take the derivative if you want to check it. I won't though. Okay.
Yeah, that's right.
Now, Arturo, you grabbed the whole thing. You grabbed all of it. 1 plus 2 sine x, it worked, right? What if someone else would have done something different? What if someone else would have, instead of grabbing the whole thing, just grabbed the sine of x and said, oh, I see its derivative right there. That would have worked also, but you would have had a longer problem because you would have had other things. You would have had another integral that you would have had to have dealt with. I'm debating whether or not we want to see that or not. Before I decide if I want to show that or not, why not choose cosine x for u? Why not choose cosine x? Because if you let u be cosine x, isn't the derivative of that negative sine of x? Dx, notice I brought the dx on the other side already. Isn't it this? And isn't that we have sine x down here? We're off by a constant, right? We have negative, but that's big deal. It's a constant, right? Why would I not do this?
Because the sign's in the denominator.
The derivative is in the denominator. You don't ever want that. You don't want the derivative of the something to be down on the bottom or trapped inside of something. So that's why it's better. Well, in this case, it's the only way to go is to choose the part with the sign in it to be your u. Let's go to a different example. I want to show you kind of a little more variety here. How about this one? Yeah. How about the antiderivative of natural log of 1 plus the square root of x over oh, wait a minute, hold on. We're not ready for this. Hold on, we're not ready for this. I'm pushing too hard. Here, let me do this instead. Yeah, sorry about that. Yeah, because we don't know the antiderivative of natural log yet. All right, I gotta keep it a little more tame here. How about this? Secant squared, or secant, yeah, secant squared of the square root of x over the square root of x dx. How is it almost 140?
No. Time flies when you're having fun.
Yeah, I guess so. All right, so again, I'm gonna call on somebody because I'm hoping that somebody is gonna get stuck. How about Nellie? I'm going off your screen name there. Are you on campus, Nellie?
Yes.
Yes?
Yeah.
All right. Are you following along kind of with what's going on here?
Kind of. I'm just like trying to understand.
So here's the deal, Nellie. You've got to step up to the plate. I don't know if you've ever played baseball. I'm not a baseball person, but you understand what I mean, right? You have to take a swing, all right? You're never going to hit the ball if you don't take a swing. So when it comes to Cal 2, this is more true than ever. You have to try something. I like to think of it, I like to tell my students, it's like, if you curl up in the fetal position, right? Nothing's going to happen, okay? Nothing will happen. You have to try something. Even if it doesn't work, you've got to try something. And that's really what we're looking for here is engineers, right? Computer science majors. This is at the end of the day, this is not about can you do these integrals? This is about presented with a challenge. Are you going to be like, forget it, I'm out of here? Or are you going to be like, I'm not going to bed till I figure this out? Like, which type of person are you, right? That's what it really comes down to. It's like a puzzle almost. Okay, Nellie, take a swing.
I'm not sure. I don't really know.
You've got to pick something and hope that its derivative is there too. And it's okay if the derivative is off by a constant. It's that the derivative can't be in the denominator or trapped. I'm gonna force you to pick something. Okay, I don't care if you're wrong. Nobody here cares if you're wrong. All right. In fact, I want you to actually be wrong if you could to demonstrate being wrong. But just try something.
The derivative of x, square x.
You want square root of x?
Yes.
Okay, let's see. Square root of x. Now, wouldn't it be helpful for everyone in here if you knew what the derivative of that looked like already in your mind? if you don't know what the derivative of that looks like in your mind, it's going to make this harder, isn't it? So hopefully you know this, that the derivative of this is 1 over 2 root x, because I told you to remember that, right? And then I'm going to put the dx on the other side. 1 over 2 root x, right? That's a derivative square root of x. Now, do you see it over here? Do you see 1 over 2 root x? Not exactly. It's there though. It's there. It's just not, it's not like glaring at you. You have to rewrite it first. You have to rewrite this as secant squared square root of x times 1 over the square root of x dx. See, because it's a fraction, right? I can slide this numerator off to the side and pull this root x out here as a 1 over it, right? Can I do that? That's just algebra. Nellie, do you see it? You see this piece here, 1 over root x dx, 1 over root x dx. We have that. We just don't have a 2 on the bottom, right? We don't have this 2. That's okay. I just multiply both sides of this by 2. 2 here, 2 here, it'll cancel the 2. And now I have this, 2 du equals 1 over the square root of x dx. Look, at this point, it's not as if we're home free, okay? We have seen something and its derivative, and we see it's here somehow. We're off by a constant. We're kind of tweaking things, and we're going to try and rewrite the integral now. This yellow part will be replaced with 2 du, and the square root of x will be replaced with u, right? That's this part. Nellie, I'm sticking with you. What would the new integral be in terms of u? We're going to switch it all from x's to u's now. So what would I have here? What would this become?
Secant squared u.
Secant squared u. Good. Times, okay, what's all this yellow become?
2 du.
2 du. Okay, now Nellie, that 2 right there is a constant, right? Pull it out. Take it out of the entire integral, put it here. And now look at this, secant squared u du, right? That's where we are. So that means, Nellie, all you have to do, since everything is cleaned up, all you have to be able to do now is tell me what the antiderivative of secant squared of u is. And I will ask, let's see, I'm trying to think, Maddie, how about Maddie? Seems like I haven't talked with Maddie in a while. Maddie, do you remember what the antiderivative of secant squared u is? Maddie may not be there. Most of y'all talked last time, no?
Wasn't
Raquel,
it
did you talk last time?
tangent u?
Raquel, do you know the antiderivative of secant squared u?
The tangent?
It's tangent, right? It's
Okay.
tangent. Good. Yes. So if you don't know that, right? If you don't know that the antiderivative of secant squared of u is tangent u, of course, in Cal 2, that's going to hurt, right? That's why in Cal 2, the better you are with your derivatives, the easier this is. If you don't know what the antiderivative of secant squared is, it's gonna cost you. It's gonna start costing you. All right. So now our answer is 2. The antiderivative of secant squared u is tangent u plus some constant of integration that I don't know. And now what I do is replace my u with the square root of x. I guess I could have put the u in, it doesn't matter. There it is. You can always check your answer by taking the derivative.
Now, would we write that as 2c or just 1c? Considering it
Good,
doesn't
good question. Yeah, the 2 here, right? So I guess what Josh is asking here is that if we just look at this part here, that should have given us tangent of u plus c, right? But then we had a 2 in front of everything. So Josh is asking, we put the 2 here and the 2 in front of the C. You could, it wouldn't be wrong to put the 2 in front of the C, but it's not wrong. You could do it either way. We don't normally do it because 2 times a constant is the same as a constant. We don't know what the constant is, right? It can be any constant. So twice a constant is still a constant. So we normally don't, we just always just put plus C. We don't distribute anything to it, or, you know, even if there's like a square root, we wouldn't even do the square root of C. We would just do C.
I have a quick question.
Yes.
Could you have brought, like, could you have taken the square root of x, made it x to the half, and then brought it up to make it secant, whatever we have there, times x to the negative half?
Yes, you could have rewritten this as secant squared square root of x times x to the negative 1/2 dx. Is that what you're saying, Anna Marie?
Yes.
Yes, you could have done that. But then
Okay.
my question would be, what now? Right? Like, what do you want to do now? You can't put these together because this is trapped in a secant. So you're not gonna be able to do anything with this.
That's the moment that you see its chain rule.
Yeah, I mean, this is chain. We are trying to undo
Yeah.
the chain rule. That's what we're trying to do.
Yeah,
is undo the chain rule.
that's what, from what I've just been seeing on the substitution, is that just what substitution is to undo mostly? Or is
Not-
it,
Yes.
is it
and
just
no.
that that's just what we've dealt with so far?
It's what we've dealt with so far. I actually have another example that is on the docket here, at least on my mental docket of things I want to show you today. Let's do it now. I think now would be as an appropriate time as any to show you something. We could do a few more like the ones we've done, but I think we can do this one. Let's check this one out. X, and then let's go with 8 plus x to the 100th power dx. Let's get some things established first. You are not allowed to push this x inside and make this 8x plus x squared. You cannot do that because order of operations says you must do exponents. You have to do that 100th power before the multiplication between these two, right? So maybe you're like, okay, well, I'll just expand this 8 plus x times 8 plus x times 8 plus. Maybe you want to do that 100 times. I mean, you could though, right? Like you could expand it. And then once you expand it, you could distribute an x through. And then you could use power rule on all those terms, couldn't you?
Yeah,
Yeah, you don't want to though, right?
no.
And even if you did, even if you wanted to do it, I would just change this to 1,000 and I'd eventually make you like, capitulate, you just like, I'm done, forget it, I'm not doing it. All right, so what do we do, right? What do we do? It's like, do we see something in its derivative? I see x, right? What's the derivative of x? 1? I see
Yeah.
ones everywhere, right? So yeah, we have it, but I mean, is that going to get us anywhere? Like if I let
I mean,
u be x?
we
Can
could-
we not set u to 8 plus x?
You could do that, right? You could do that, but it doesn't maybe initially doesn't seem like that's going to help, right?
I mean,
But
it
look.
would effectively kill off our exponent of 100.
It'll do something. So look,
Yeah.
you gotta take a swing, right? Gotta take a swing. So Anna Maria is suggesting we do u equals x plus 8. I don't want you to think that this is like guessing. It's not guessing. There's thinking that should be happening here. Using the u as x plus 8, the thought here is this. The derivative of that is 1. And I've got a 1 here, right? But by replacing x plus 8 with u, now I have u to the 100th power, right? And that doesn't have to be expanded. Let's keep going. I take the derivative of this. and I get 1 dx. Again, remember, I'm bringing that dx over. Don't forget the dx. I'm doing du dx equals 1, and then I multiply both sides by dx. All right, y'all good? Understand so far? So here's the way I'm going to look at it. There's a 1 next to that dx. Okay, so I've got this matches with this. I'm dead on exact match, right? I've also got x plus 8 is 8 plus x. Oh, I wrote it the other way. Big deal, right? Those are the same. So that can be replaced with u. But what about x? What do we do with that? We can't leave x there. We've got the other two are going to switch over, but the x is, we can't have u's and x's mixed together here.
Could we also substitute it out?
Nope, don't make another substitution.
Hmm.
So what we're trying to do is we're trying to take this integral that had x's in it and create an integral that has u's in it, right?
You replace it with u minus 8.
Ah, okay, so we take this equation and we solve for x. Right? Just solve that for x. Subtract 8 on both sides. And what do you get? U minus 8 is x. And so now you have an equation for x that has u in it. So I'm going to replace this green with u minus 8. I'm going to replace the blue with u, and I'm going to replace the 1 dx with du. And I'm going to look at this new integral, and I'm going to hope it got better. So x is going to be replaced with u minus 8. I need that in parentheses. Then I have the blue part to the 100th power. That's u to the 100th power. And then the dx gets replaced with du. And then you look at this and you're like, well, did we gain anything? Did this make life better at all?
Yeah, now we could actually distribute that now.
This can be distributed. Y'all see that? Because the u minus 8 is not raised to anything. So I can distribute that through. Right? Do y'all see that? Just distribute it through. This becomes u to what power? U
The
times u to the
101st.
100 is u to the 101.
Yeah.
Minus 8 times u to the 100th power du. You have subtraction between two terms. They're both raised to powers. You can use the power rule now, right? Just the power rule on each one. So my antiderivative, I'm ready to go to my antiderivative, is going to be the antiderivative of u to the 101st power, which is 1 over 102 u to the 102 minus 8 times, now the antiderivative of u to the 100th is 1 over 101 u to the 101 plus c. That's power rule on both of those. Almost there.
We just got to
Last
substitute
step.
in our use.
Replace u with what it was, x plus 8 to the 102 minus 8 over 101 x plus 8 to the 101st power plus c. This is the antiderivative. So I brought that problem up now because Hunter was asking or kind of mentioning that it seems like what we're doing is undoing chain rule with substitution, which in many cases we are. But this is an example of where we're not really undoing chain. I mean, we are, but it's not obvious that we're undoing a chain rule here. Because if I ask you to take derivative of this, it's hard to believe that the derivative of this is that, right? Isn't that kind of hard to believe? That the derivative of this gives you this? I'm going to prove it. Ready? Y'all are all about to get through this class, right? Cal 1, so y'all should be able to take derivative of this.
Yeah, derivatives
Here we go.
mostly easy.
Here we go. So I have two terms, this one and this one. Here we go. First thing, I need chain rule here, right? So the 102 comes out, up, the 102 kills it. That leaves me with an x plus 8 to what power? I'm
One
differentiating.
first.
100 first. Okay, minus, now the 101 comes out, right? And it cancels with the 101 there, and I have an 8 left. So 8, and then I have x plus 8 to the 100 power, right? That's the derivative, right? Now, how is that up there? Well, factor out of both of these an x plus 8 to the 100th power. So if you take x plus 8 to the 100th out of this one, you'll still have one x plus 8 left here, won't you? So I'll have an x plus 8 there. And then you took all of these out, which leaves you with what here?
-8.
-8. And the 8's cancel. And so you get x plus 8 to the 100th power times x. And that's what the original integrand was, right?
That's
So
pretty
it
good.
Works. It better work. I mean, because that's our answer. So it better be right. As you might imagine, this can start to get pretty crazy, right? Pretty crazy. All right, let's do another one. X E Yeah, this one won't be so bad. That's a very basic one. Why don't I give you a minute to see if y'all can kind of figure this one. I'm going to give you a couple to do, just to kind of practice with. That'll be your first one. Okay, I've given you 3 problems there. Actually, I think number 2 is the hardest one there. So if you get stuck on 2, maybe move to 3. What do you say? I give you all, I don't know, 5-6 minutes, see what you can do. All right. I know it hasn't quite been the full time. So how about the first one? Who's struggling? Come on, there's no shame here. You won't have to see each other again. Who's having trouble with the first one?
Having trouble with all of them.
All of, okay, so Daniel, let's
suck.
let's go with Daniel. Look at the first one. All right. Do you see anything that when you take the derivative of it, it's also there somewhere?
No, sir.
Okay, so let's just start looking piece by piece. How about x? You know derivative of x? Daniel?
I'm not good at this. I need more practice. So
I think you're overthinking it. My question is just, what is the derivative of x?
that's just one then.
Yeah, 1. Okay, so there's definitely a 1 here, right? There's 1 everywhere, right? There's 1 there, there's 1 there, so maybe we could let u be x. All right, how about the next piece that's kind of clumped together? How about x squared plus 1? You know derivative of that, Daniel?
Just 2x.
2x. Okay, do you see a 2x anywhere?
No, sir.
Okay, but you do see an x, right? It's just not a 2x. That's okay though. It's okay to be off by a number. You just have to have the main part of it is that the X part is there. So that looks promising. Does that make sense, Daniel? That if we let U be the X squared plus 1, the derivative of it appears to be there somewhere.
No, not really. I still don't get it. I really don't understand it right now.
Okay, that's fine. Who else was struggling with this?
Yeah, I was struggling to find it because wouldn't just
Okay.
e to the x squared plus 1, that's itself, wouldn't we also be able to use that for u?
And then just take the derivative of that.
Would U be the whole thing with the E?
Yes.
The whole thing. So that's another, okay, so let's try that. If we were to take the whole thing, think about that. So I'm mentally thinking about this. What would the derivative of this be? Chain rule, right? The derivative of that would be itself, right? Times
2x.
what's up there, which is 2x, and then you have
dx.
dx, right? So look, you've already said that this piece in blue is u, right? So this is off the table, all right? That's off the table because you're going to replace it with this. Got it? Now you need to be able to see its derivative. Here's the derivative. You need to see it here. Well, this is way too much. Do you see that? Like you've got, okay, yes, you've got the x dx, I agree with you, but you've got all this other crap in here too. That's not a constant. You're off by more than a constant there. You're off by an entire function. That makes sense to you?
Yes, it does. Okay.
So it's like you took too much here. You grabbed too much because you grabbed the E as well. So instead, let's just grab the, come on, man. There we go. Let's just grab the x squared plus 1. Let's grab that. Just that. This is what Daniel we were talking about this. We said, okay, if we let u be that, the derivative of that is 2x dx, which I do have here. You have to see it though. I have x dx, x dx. This part here, this x squared plus 1, that's up there, right? So if I rewrite my integral, I'm going to rewrite the integral first. I'm not going to substitute anything yet. I'm just going to slide things around. I went ahead and moved that x back here with the dx so that I can see the x dx like that. I've got my u here. I've got u here. That's my u. I'm off by 2, right? This 2, don't have it here. So I can always fix that. I can get rid of the 2 by multiplying both sides by a half. At this point, we can do our substitution, right? This part in blue is going to turn into half du, and this part in yellow is going to be replaced with u. So e to the u times, let's see, 1/2 du. The 1/2 can come out. I'm going to move this over here. Are there any questions on what I did here? Letting the u be this, moving things around, substitution.
I got a question. Like, I mean, you can continue with this part. I'll just like once you're done with the problem.
Okay, so now what's the antiderivative of e to the u?
E to the u.
Itself, right? There, the antiderivative is itself. So if we do e to the u here plus c, so we have to, again, from earlier in this class, we have to remember that the derivative of e to the x is itself, so the antiderivative of e to the x should be itself. In this case, we're using u and not x. And then the last thing is to replace u with what it was, and u was x squared plus 1 plus c. I think you have to do like, 100 u substitution problems before you start to really get comfortable with it. Before you
believe it.
start to really feel like, okay, I think I've got this now.
Yeah, I'm starting to see it. Like the first few problems, I was like, I'm trying to follow along, but this
Yeah.
one's, I mean, it's an easy problem, but seemed easier.
Now that you see it, right?
Right.
Now that you see it. How about this one? Let's skip the second one. This one's,
The second one's the one that tripped me up.
yeah, the second one's tough. I was reaching a little bit too much on that one, I think. But the second one is actually a problem very similar to something right out of the book. So it's not like I'm going crazy on you here. So I'm not going to let, here's what I'm thinking. I'm not going to let u equal e to the 1 over x. The reason I'm not going to do that is because the derivative of this would involve another e to the 1 over x. And I only have one of them here. So I'm not going to do that. So e to the 1 over x is too much. What else can I maybe consider?
1 over x.
1 over x would be a consideration. So these are some things I can think about. Maybe 1 over x. How about x squared?
You could, but it doesn't work out.
What's the derivative of this?
2x.
2x dx. And do I see an x? Do I see an x somewhere? I see an x right here, right?
Yeah, but isn't that considered trapped up there in the exponent?
That would be considered trapped because it's inside the exponent of the exponential function, right? It's in the denominator of a fraction that's the exponent of the exponential function. It's trapped. I can't easily get to it, all right? So this doesn't look like it's going to work. What about this one though? 1 over x. What's the derivative of 1 over x?
Negative 1 over x
negative
squared. And it's
Negative 1 over x squared. Now it's, again, isn't it very helpful to know that just right off the top of your head, not needing to like write it down? The derivative of 1 over x is negative 1 over x squared. Do I have negative 1 over x squared?
If you
Not
break apart your
exactly.
fraction.
Yeah, it's a little, I'm a little bit off, but it's here. If I pull that fraction apart, put the e to the 1 over x out front and write that x squared on the bottom like this, then this looks like this, doesn't it? Except for the negative. That's okay. I'll multiply both sides by negative 1. That'll kill off the negative. So that means negative du equals 1 over x squared dx. And now it matches. This matches with this. And 1 over x is the u. U to the u times negative du. Replace the blue with this. Replace the 1 over x with u. This negative here is like a negative 1, so I'll bring it out. And now I've got a very simple antiderivative. The antiderivative of e to the u should be itself. So this will be negative 1 times e to the u plus a constant. And then I'm just going to put a negative, not a negative 1. E to the, what was u? It was 1 over x, right?
1 over x, yeah.
Yeah, plus c. That's it.
Sweet.
That's the antiderivative.
I was off by a negative sign.
You got that, yeah, negative on that. On that
I forgot.
derivative.
I forgot that negative would come out net. That derivative would come out negative.
Yeah.
I think think I might have figured out number 2.
Oh, good. Okay, so let's see. Let me go grab it.
Okay, so I'm not sure if I'm right, but what I did is that on the top in the numerator, I changed it to 2 sine x cosine x because of the double angle formula.
Now, is there a reason you did you just do that right off the bat, or did you do something first and then decide to do that?
Well, first I tried substituting u for sine 2x, but once I did the derivative, it didn't work.
Okay.
So then I noticed also you can change the denominator on the bottom to, that's just, isn't that one of the Pythagorean identities? So
Well,
that,
if it was subtraction,
oh, if it was subtraction.
well, if it was subtraction, it would become sine squared.
Right, okay, that's what I messed up.
Did you make it sine squared and then cancel a sign?
No, I made it sine squared x, and then I did u is equal to sine squared x.
Got you. Okay, you're on the
Okay.
right track. You're on the
So-
right track, but you can't do the Pythagorean identity here.
That
Yeah.
actually solved the problem I was having is if you do the double angle theorem on the top, then 2 sine x cosine x, that's the derivative of 1 plus cosine squared x. So you can do
Yeah,
the substitution.
Yeah,
Okay, so then look, again, this is, I cannot stress this enough going into Cal 2. I cannot stress this enough. The more you can see when it comes to derivatives in chain rule, the more you can see, the easier this becomes. So when you look at this and you think, so forget Anna Marie, this is good, okay? But let's act like we don't know this yet, okay? If you were to say to yourself, all right, look, I'm gonna let you be that, okay? And I'm writing this down, but I'm more thinking about it mentally. Okay, I'm like, okay, if the bottom is u, what is the derivative of that, right? That's what I'm thinking. And I'm like, okay, well, the derivative of 1 is 0. So I don't need to worry about that. But then I have to take derivative of cosine squared x. And that's a chain rule, right? So we're going to have a 2 come out, cosine x, times now the derivative of cosine, which is negative sine of x. Yeah? That's what the derivative of u would be. Dx, I need a dx out here. So this would become negative 2 cosine x sine x dx. That's what du is. And so you may initially give up on the problem, or not give up on this as a u substitution, because you're like, well, wait a minute. If this is u and this is the derivative, I don't have that anywhere, right? I don't have that anywhere, until you realize that this double angle formula for sine 2x from pre-cal is 2 sine x cosine x. And now
which is,
they're
that's only
pretty
by
much
negative
the
1.
same, right? Except they're off by sign. So you could rewrite the original integral as this: 1 over 1 plus cosine squared x times 2 sine x cosine x dx. All I'm doing is peeling this apart, taking this, putting it next to the dx, creating a fraction out of this. I'm realizing that this 2 sine x cosine x dx matches this right here, except the minus sign. And then the entire denominator is my u. I need to resolve this minus sign. So I multiply both sides by -1, turns that to a plus, turns this into -1. And then I rewrite the integral. Integral 1 over, the blue part is u, the yellow part is -1 du. Take the -1 to the outside, I've got 1 over u du. And that gives me negative natural log absolute value of u plus c, because the antiderivative of 1 over u is natural log. We've been through this today. And then we replace the u with 1 plus cosine squared x plus c. So Anna Marie, when what you did, you use a Pythagorean identity the wrong way, but then you let u be the sine squared, and then the derivative of that was very similar to this. And then you went and did double angle. So there was just that one little minor thing of that this wasn't a minus. So there's the antiderivative. I hope that just going through this, you're starting to see that, you know, when you think about Cal 1, you think about product rule, right? Remember when we were learning the product rule? It was like, oh, if you have two functions and they're being multiplied and you take the derivative is f prime times g plus g prime times f, right? Now that you can like reflect on this a little bit, that is very mechanical, right? As long as you get the derivatives in the right place and, you know, position them f prime then g then plus g prime then f, it's pretty systematic. There's not a whole lot that you have to really think about other than taking the correct derivatives, right? And then same with quotient rule. It's like, okay, you know, there's a rule for it, right? And then chain rule is a little more involved. You have to think about composition, but at the end of the day, it is just an operation that you do. Not here, right? Not this. This is, there's more here, okay? There's more thinking involved here. There's more understanding, there's more trial and error, there's more, it's not just monkey see, monkey do, right? It's, you've got to think about things. This U substitution, like I said last time, is the first of 5 techniques that we use, 5 methods, 5 approaches. U substitution is the easiest by far the easiest, all right? So you can start to get a feel for like, wow, this stuff starts to build very quickly. And that's why in Cal 2, we always like at least at Northwest Vista, we like to go through the 5 techniques of integration first, because that's gonna kind of like see what you're capable of. All right. Some colleges, what they do is they go through and they talk about antiderivatives and they get into like the geometric meaning of it first, and students do pretty good with it. And then they do the techniques later, and then the students are like, it's a disaster, because you're like a third of the way through the semester and it's like, oh my God, where did this come from? So we do it, we're right off the bat, like we get right into the techniques, and then you start to really, you know, feel challenged.
Open with a sucker punch.
Yeah, open with, well, it's a marathon that you have to run. Okay, that's Cal 2 is a marathon you have to run. You can't jog it, you can't, but it is what it is, you know, it's I had to go through it. Everyone that, you know, it's doable. Okay. I mean, people get through Cal 2. I'm not trying to scare you. I'm just trying to prepare you for it, because it's really different. It really, really is. So, all right. I want to just kind of end on a couple of things. I'm not going to have time to get into the real long drawn out thing that I wanted to, but I'm just going to show you the end result. On the review, oops, no, didn't mean to do that. On the review here, the last 2 problems are U substitution problems. These are find the antiderivatives, and they're U substitutions. So you got to look in here, you got to see something and its derivative, something and its derivative. So I intend on testing on this concept because I've spent time on it. So now the rest of this, the rest of what I want to say today is just to kind of bring this together. So what we have, the reason why antiderivatives are so important, the reason why they're so vital to us is this. I'm going to do this with an example. I should have enough time. Let's take a look at the function f of x equals, let's go with 3x. All right. And I only want to look at this on the interval, let's say 0 to 2. Okay. I'm going to draw this for you real quick. This function, if you plug 0 in, you get 0. And if you plug in 2, you get 6. And it's a straight line, isn't it? 3x is a straight line. So it's this right here. That's the function looking just on that interval. I would like for you to consider if we were to just look straight down from this point to the x-axis, what would the area of this be? What would be the area of this region below this graph? Can you do it just by looking? Do you know how wide it is? How wide is this?
It's two across and 6 tall, and then
Divide by 2.
Pythagorean the other side.
Yeah, so you just need the area of a triangle, a right triangle. What's the area of a right triangle? 1/2 base times height, right? Half of base times height. So this would be half of the base, which is 2, times the height, which is 6. That should just give you 6, right? That should just give you 6. Yes?
Yeah.
Do you agree with that? The area of that is 6. All right.
Yes.
Big freaking deal, right? All right, now here, do this. I'd like for you to tell me what the antiderivative of 3x is. What's its antiderivative?
3/2
right?
x squared.
It's 3/2 x squared, right? 3/2 x squared. That's the antiderivative plus a constant, right? Plus a constant. Great, wonderful, right? Big deal. Now this is the part that's really mind-blowing. I want you to take this answer, and here's what I want you to do with it. First, what I want you to do is take the right endpoint, which was 2. I want you to plug 2 into that. And then I want you to take the left endpoint, which is 0, and I want you to plug 0 into it. And I want you to subtract the answers. Okay, so let's first start by plugging in 2. So I go 3/2. I'm going to go 2 squared. Okay, understand? I'm plugging 2 into this answer. And then over here, I'm going to go 3/2, 0 squared. Now, the one on the right's easy because that's just 0, right? What about here? 2 squared is 4?
4.
4
That's
times 3?
4 times
12,
12
then
over 2,
12
so
to-
6.
6. And 6 minus 0 is 6, right? This is not a coincidence. This is not a coincidence that we got this. This is what's called the fundamental theorem of calculus, a version of it. We can find the area under any curve by using the antiderivative. Now, I did it for this curve, 3x, because I could show you visually that this, like, we know how to find this area, right? Because it's just a triangle. So we could confirm that it worked, all right? But now let's take a look at a function that's not a triangle. How about this? What if we look at f of x equals x squared? Let's do it on the same interval, 0 to 2. If we graph this, you plug in 0, you get 0, right? You plug in 2, you get what? 4? But it's a parabola, right? This is a parabola, so it goes like this. It's curved, right? That's terrible. It's not a straight line, it's curved, yes? So if I want to know the area under this, it's not possible for me to get it using a triangle because it's not a triangle, right? But it would be nice if we could figure out this area. It would be nice if we could. What I'm telling you is this. If you take the antiderivative of this, in which case here you get 1/3 x cubed, oops, 1/3 x cubed plus c, right? That's what you get. If you take this antiderivative, plug in plug in the right endpoint first, plug in 2, plug in 0, into this, that will give you the area. Subtract the two answers. So that means you plug in 1/3 2 cubed, and then 1/3 0 cubed. What do you get here?
8/3.
8/3.
8/3. The exact area underneath that curve is 8/3. All right, now I'm not proving this to you. I'm telling you this is where we're headed. Okay, so what we do is in Cal 2, what we do first is we say, let's make sure you know how to find antiderivatives first. Okay, let's make sure you know how to do that, and then we start applying it to something. So when would you ever care to know the area under a curve, right? When would that ever be important? Well, think about this. Let's say I give you a function where this is time and this is velocity. Okay, so I'm measuring the velocity at every point in time. Think of it like your speedometer. You're just looking at what your speedometer is doing. All right. So you start a drive and then you're keeping track of your speedometer. So your speedometer does this and does that, and then you come to a stop, right? Your velocity at the beginning was 0, you sped up, slow down, sped up, slow down, and then you get to the end, right? What do you think the area of all of this would be?
You mean like the number value or like
What would it
the actual
represent?
point of
Like,
it? Yeah,
what would it represent physically?
I have no idea.
Okay. All right. Well, let me do it this way. If I'm telling you that we're going to somehow use the antiderivative, right? No, I don't want to do it that way. Do it like this. I'm almost out of time. Do it like this. Imagine just a little small sliver of this right here, a little small sliver of that. Okay. If I wanted the area of just that little sliver, this right here would be a measurement of time, wouldn't it? This little left and right would be a measurement of time. And what would this be? A measurement of
Velocity.
Velocity, right? Speed, velocity. So if I find the area of that, I'm taking the velocity and I'm multiplying by time. So think about a velocity. Give me what units do we usually use for velocity? Like when you're driving your car. Miles per hour. So this is going to be some measurement in like something like miles per hour. And we're going to multiply it times what?
Time. Probably
Time,
also
which
an hour.
we're measuring in hours, which means that the hours cancel, which means you're left with miles.
So
In other words,
the
it's
distance.
measuring the distance you traveled. The area under this curve is a measurement of the total distance you went. So that is a very different way of looking at things. Everything we've done has been something different. We've been doing slopes of tangent lines. In Cal 2, we look at curves and we look at areas under those, and then those can have all sorts of physical meanings depending on what class you're in. If you're in a physics class, you might have something like time, and this might be force. So you're applying a force to an object over time, and you're measuring that, right? That force you're applying to an object. The area under this would represent work. The amount of work you did. That's what it would be. It would be basically this unit times this unit, force times time, or sorry, distance is what I meant to say, distance. It doesn't matter. There's a lot of different things you can do. All right, well, we have 5 minutes. We don't have a lot of time to talk about the finals. So I tell you what, if I have an opportunity next week, I will, I don't know, if y'all come up with like a group that is going to do like a study session or something like that, like Zoom. I don't know. Are y'all using Zoom for study sessions at all? Anyone?
I have not.
Done in the past, yeah.
Yeah. So if y'all put together a study group or something where you're going to have, a group of y'all together studying, just shoot me up with a text or something and let me know. And if I'm free, I can join to drop in and answer questions if you'd like. If I'm free. Next week, office hours are going to be different because when we get finals, we're in class twice as long as we normally are. So when I normally have a break, I'm not necessarily going to have a break. So for next week, office hours, I'm going to have to send y'all out an availability. But really just, again, text me, email me or something if you're trying to get some help. Any questions?
Yes, sir.
All right, I think we've come to the end of the road here.
I have a
Well,
question.
actually, I do have a question.
Yep.
Are we gonna be doing like the entire test like for 2 hours and 45 minutes?
You'll have whatever it is, 2 hours, 45 minutes. That's how
So
much
like,
you'll be given.
okay, and are we expected to use the entire time for like the entire test?
And are you expected to?
No.
I mean, are you asking me, will it be that long?
Yeah, this is kind of what I'm asking.
I think that'll depend on you, right? I mean,
Okay.
yeah, some student, there might be someone that finishes in an hour and a half, and there's someone that, if I gave them 8 hours, they would take 8 hours because they would always want to check something, right? So everyone's different. I'm going to try and make the test where I believe a student that should be passing Cal 1 should get through the test in 2 hours, 45 minutes. Right, that's kind of the whole. Yeah.
Wait, so then like how many questions would be on it? Because I know it's definitely not going to be 10, 11 or something.
Yeah, well, I have to write it first before I can tell you how many questions are on it, but like I said, it'll be what I expect you should finish in one sitting, 2 hours and 45 minutes. Let's see, how long is the review? Do y'all think this review is too long? Like, do you think this review could be a final?
14 questions, right?
Well, look at them though, I mean, like, if you have to have tried this already, right? So
They mostly we have 200 minutes total.
yeah, roughly.
That doesn't seem awful. 17 questions in 2.5 hours seems reasonable.
Yeah.
That one's
think
going to be funky.
You're going to have to kind of, when you get to the test, you're going to have to kind of, I always say, don't just start grinding away on number one. Like, look at the whole test first, kind of figure out what you feel good about, and then, go after the things that aren't going to take you forever. And if you ever find yourself spending more time than you think you should be, it's better to cut your losses and move on. It's never a good idea to get hung up on a problem for 30 minutes. It's never a good idea. It's always better to just move on, because if you do 30 minutes, you might not get to 4 problems, right, for getting 1 problem right, as opposed to skipping that problem and getting 3 others right or 4 others right. So, yeah.
And related rates will be on there.
Related rates, was it on here?
I think it was on the other review you sent out.
Yeah. Yeah, so, I mean, it's all fair game.
Sweet, I'm going to get at least 2 questions wrong on this. It's funny because we had all this time, and you know what I always think of whenever we're talking about length of test compared to time we have? My brain always goes back to the ACT, where there's simpler problems, but you get 60 problems and you have an hour to do all of them.
Yeah.
It's like, oh yes, I'm that fast at any math.
Yeah, those standardized tests, a lot of that is just about learning the strategy of taking that type of test, right? Like, instead of like actually getting the answer, like looking at the 4 options and like eliminating 2 of them and then like flipping a coin on the other 2. I mean, it really is about test taking as opposed to like knowledge. Yeah.
E on every answer.
All right. Well, y'all are free to go.
I had a question.
Yes, sir.
Could I get today's lecture and last class lecture, please?
Yeah, I realized someone told me that I accidentally posted my college algebra lecture on our thing. So double check, that should be posted. What do you call it? The last class's video should be posted. And then I'll post a video after class and I'll send the notes right now. What's today? 12/2?
I have a quick question.
Mm-hmm.
Do we have any homework assigned besides the ones assigned on Tuesday?
The review, if you want to look at stuff from 5.5 out of the textbook has more problems with substitution if you want to just practice stuff.
Okay.
Yeah,
Thank you.
5.5. Current section, and it's making sure it's going there.
Do you have a piece of paper hanging over the top of your camera?
Yeah, you know what? No, hold on. I don't know what. Yeah, there we go.
Just looking, and I noticed that. That was funny.
Yeah, no, it's a light that I have above my desk, and it's too bright, so I have a piece of paper covering the light. All right, Daniel, I'm pretty sure I'm looking right now at the playlist for our class, and 11:29 should be here now. Take the derivative. Yeah, so this is last class. Derivative of x is.
Thank you.
Yep.
I had another question. You said we'd get extra credit for showing our homework and I guess for showing our faces on here. How much was
Yes.
that actually, like, in total?
Well, what it's going to be is like when your final grade comes out and you're like, you know, you need that extra point to get to the next letter grade, that sort of thing. I will take all that into account. It's not going to turn you from an 83 to a 90 in the class. You know what I'm saying? Like, but it will help push you over the hump if there's a hump. Now, I had this talk with my class earlier, my other class earlier today, like what are realistic expectations when it comes to extra credit, right? Like, and what are realistic expectations when it comes to your grade in terms of rounding, right? Like, of course, if you get an 89.5 as a final grade, I'm going to round it up to an A. It's going to be a 90, right? But like, where do I cut it off? Am I really like anal about it? And am I like 89.4? Sorry, you get a B, you know? That's where the extra credit and the homework comes in. It's like, okay, you did that part, we got that, it's justified. The danger is when I get into positions like this, you'll have a student who has, I don't know, maybe they have a 77.8, right? That's their overall grade in the class, right? So they needed really a 79.5 to get the B. So in their minds, they're only what, like, how much more do they need? 1.7 points, right? Something like that, 1.7. That's all they need. So in their minds, they're like, hey, you know, I just need 1.7 points. And then that's enough. What can I do? Blah, blah, blah. Well, if you have your homework and you've been on video, you know, for the class, been participating, then we can talk. But I have to have something to justify it. I have to have something to justify it. I will not just award a student 1.7 points for nothing. And here's why. If I do that, I have to do it for everybody, right? Across the board. You'll never, no matter who you talk to, I've been teaching for 20 years, you will never hear of a student who ever got a curve on anything without everybody getting that same curve. Like a free points. Like, I just don't do that. It's just about fairness. So if for some reason, like you weren't on video, you didn't do your homework, whatever, if you don't have any of that and you want that extra 1.7, then, well, sorry, you're not going to get that 1.7. And there's a reason for it. It's a snowball effect. If I give this 1.7 to one student, right, I give it to all of them. And then the student that was like at a 75.8 is now closer to the B, and they feel like, you know, because, right, if I give them 1.7 points, now they've moved up, And now they look at the B as, oh, all I need is another 1.5 or whatever for B. What can I do? And it's just like everyone gets shifted up, everyone gets closer to the next letter grade, and there's just no, where do you stop it, right? Where do you stop it? So I have to be somewhat rigid when it comes to the grades, but the homework in the video will help you in any case where we're on a borderline. I'll be honest, what I love to see are grades that land like right at the bottom of a letter grade. I love seeing that when I do my final grades. If a student has a 91, boom, they're A, you know? If they have an 81.4, that's a B, you know, it's easy. It's when it's it's right there on the border of the 2 grades. That's when we have to start talking about it. So I hope I'm addressing your question.
I mean, I thought that the extra credit was just going to be some points on the exam, not something like that. But okay, I get what you're saying, though.
Well, it is points on the exam, but how many points, right? How many points is kind of, that is subjective. Well, I guess that's up to me, right? That's up to me. I want to be able to help you all, but I'm not going to be ridiculous about it. I'm not going to make C students become A students. I mean, there are A students and there are C students, right? I mean, there's a difference between the A students and C students. It makes no sense to move all your C students up to B students. What do the A students become then, right? Like, you can't do that, right? You can't inflate everything. Not everybody's an A student.
You want us to pass, but you want us to pass legit.
Well, I think that the grade should be a measure of, well, what it traditionally was supposed to be to me, which is a C means average. Okay, there's nothing wrong with being average. Most of us are average at everything. Okay, most of us are average at everything. All right, that's the law of large numbers. I mean, there's always going to be a mean. There's always going to be an average. Most of us are in the middle of most things in life. Okay, but then we excel at other things, right? So in math, if you're an A student, you should excel. You should be, well, C is average, B is above average, and A is exceptional, right? You're separate, you're different than the rest of the group. Just like a D is below average and an F is, you are exceptional. You are different than the rest of the group. You're not capable of doing that the way those others are, right? So that's the way, to me, letter grades work in my mind. Average, above or below, exceptional, exceptional. So any sort of grade inflation to me is, it takes away from that, right? If you move your average to an A, then what's average? Is everybody great? No, sorry. I mean, you're all great, but you know, it just doesn't work like that. So anyway, we're getting off on other philosophical topics here now, but all right.
Thank you, sir.
Yeah, thank you all for your participation. I know this Zoom thing is still, you know, we're doing the best we can here, but I appreciate you showing up and participating and tolerating this whole thing, and maybe I'll see y'all down the road on campus somewhere.
Good question. Do you teach calculus too?
I'm doing 2 sections in the spring. I'm doing an internet one, and I'm doing I think it's another Zoom. Unfortunately, my only damn thing, my schedule's all messed up next semester. It's a mess. Yeah. I was only able to do 1 on-campus class, and it's like a college algebra. It's because it's probably the same thing that y'all are dealing with. If you're trying to enroll in classes, it doesn't make a whole lot of sense. Maybe for you it's a little easier, but you know, to do a Zoom and a face-to-face the same day is for me, that's hard because I have to Zoom from home. I can't Zoom from my office because we share offices, so we can't all be in there Zooming at the same time. So I have to either be fully online or fully Zooming that day or fully on campus that day. And just the way my schedule worked out, that's all I could do. So yeah, two Cal 2s in the spring.
I was wondering because, like, if I could, I'd like to take yours.
Yeah.
Because, yeah. And if I can't, do you have anyone you recommend?
There's only a few of us who do Cal 2.
Well, Hunter, I'd say I'd recommend registering as soon as you can because I'm signed on for the online course and it was filling up last time I looked.
Okay, yeah,
Yeah,
I'm probably
online.
gonna take care of that over the weekend.
Yeah, the,
classes get filled really fast.
well.
End of the
it-
semester